Diffraction of light. We know that generally light travels in a straight line. Because of this, if an opaque object lies in its path, a shadow of the object is formed. But light can bend under some special circumstances. Refraction of light. Take a transparent glass and fill it with water. Dip some portion of a pencil vertically in water and observe the thickness of the portion of the pencil. The portion of the pencil inside the water appears to be thicker than the portion above water. Now keep the pencil inclined to water surface and observe the thickness. Here the pencil appears to be thicker and also appears to be broken near the surface of water. These effects are created due to the change in the direction of light while coming out of water. So, light changes its direction when going from one transparent medium to another transparent medium, and this is called the refraction of light. Now keep a glass slab on a blank paper and draw its outline PQRS. Draw an inclined straight line on the side of PQ so that it intersects PQ at N. Pierce two pins vertically at 2 points A and B along the line. Look at the pins A and B from the opposite side of the slab and pierce pins C and D vertically so that the images of A and B are in line with C and D. Now remove the chip and the pins and draw a straight line going through the points C and D so that it intersects SR at M. Join points M and N. Observe the incident ray AN and emergent ray MD. The first refraction occurs when light ray enters the glass from air to N on the side PQ. And second refraction occurs when light enters air through glass at point M on the side SR. For the first refraction, the angle of incidence is I, and for the second it is I1. The angle of refraction at N is R. Now I1 is equal to R, and in the second refraction the angle of refraction is E, which is equal to I. On both parallel sides PQ and RS of the glass slab, the change in direction of light ray is equal but in opposite direction. Thus, the light ray MD emerging from the glass slab is parallel to the incident ray AN on the side PQ of the slab, but the emergent ray is somewhat displaced with respect to the incident ray. Now, laws of refraction. Incident ray and refracted ray at the point of incidence N are on the opposite sides of the normal to the surface of the slab at that point. That means CD, incident ray, refracted ray and normal are in the same plane. For a given pair of media, here air and glass, the ratio of sin I to sin R is a constant. Here I is the angle of incidence and R is the angle of refraction. Then refractive index. The change in the direction of a light ray while entering different media is different. It is related to the refractive index of the medium. The value of the refractive index is different for different media and for different colors for the same media. It depends on the velocity of light in the medium. Sin I upon sin R is equal to constant is equal to N. Here N is the refractive index of the second medium with respect to the first medium, and it is called as Snell's law. Let the velocity of light in medium 1 be V1 and in medium 2 be V2. The refractive index of the second medium with respect to the first medium 2 and 1 is equal to velocity of light in medium 1 v1 upon velocity of light in medium 2 v2. Similarly, the refractive index of medium 1 with respect to medium 2 is 1n2 is equal to v2 upon v1. If the first medium is vacuum, then the refractive index of medium 2 is called absolute refractive index and is written as n. When a light ray passes from a rarer medium to the denser medium, it bends towards the normal. When a light ray passes from a denser medium to a rarer medium, it bends away from the normal. And when a light ray is incident normally at the boundary between two media, it does not change the direction. That means it does not get refracted. Now, twinkling of stars. The effect of atmospheric conditions on refraction of light can be seen in the twinkling of the stars. Stars are self-luminous and can be seen at night in the absence of sunlight. They appear to be point sources, and as the density of air increases with lowering height above the surface of the earth, the refractive index also increases. Starlight coming towards us travel from rarer medium to denser medium and constantly bends towards the normal. This makes the star appear to be higher in the sky as compared to its actual position. And the apparent position of the stars keeps changing a bit because of the motion of atmospheric air and changing air density and temperature. But we do not see twinkling of planets because the planets are much closer to us as compared to stars, and therefore they do not appear as point sources but appear as a collection of point sources. So the average position and total average brightness remains unchanged and planets do not twinkle. Now, dispersion of light. Light is electromagnetic radiation and wavelength is its important property. The wavelength of radiation to which our eyes are sensitive is between 400 and 700 nanometer. The red light has maximum wavelength that is close to 700 nm, while violet light has the smallest wavelength close to 400 nm. Remember, 1 nm is equal to 10 raised to minus 9 meter. The velocity of light in a medium depends on the frequency of light, and thus different colors travel with different velocity, and therefore the refractive index of a medium is different for different colors. When white light enters a single medium like glass, the angles of refraction are different for different colors and emerges as a spectrum of 7 colors. The process of separation of light into its component colors while passing through a medium is called the dispersion of light. Sir Isaac Newton was the first person to use a glass prism to obtain sun spectrum. Among the 7 colors, red bends the least while violet bends the most. Then partial and total internal reflection. When light enters a rarer medium from a denser medium, it gets partially reflected. That means part of the light gets reflected and comes back into the denser medium as per laws of reflection. This is partial reflection. The rest of the light gets refracted and goes into the rarer medium. As light is going from denser to rarer medium, it bends away from the normal. So, the angle of incidence is smaller than the angle of reflection. If we increase I, R will also increase according to Snell's law, and for a particular value of I, the value of R becomes equal to 90 degrees. This value of I is called the critical angle. For angles of incidence larger than the critical angle, the angle of refraction is larger than 90 degrees. Such rays return to the denser medium. Thus, all the light gets reflected back into the denser medium. This is total internal reflection. We can determine the value of the critical angle like this: 1n2 is equal to sin I upon sin R. For total internal reflection, I is the critical angle and R is 90 degrees. So 1n2 is equal to sin I upon sin 90 degrees is equal to sin I, as sin 90 degrees is equal to 1. Rainbow is a beautiful natural phenomenon which is a combined effect of dispersion, refraction and total internal reflection of light. It can be seen mainly after a rainfall. Small droplets of water act as small prisms. When light rays from the sun enter these droplets, it gets refracted and dispersed. Then there is internal reflection, and after that once again the light gets refracted while coming out of the droplet. And all these processes together produce the rainbow.